Okay, so now let's jump to start our first lesson on gravity. Go ahead and share my screen. All right. We are going to start off today by doing a little pre-learning activity. So if you guys would actually turn to the back or turn to the second page, I believe, you're going to find these 15 or these 10 questions in a little true or false section. Now, I don't expect you to know any of these off the bat. These are just things that I want to see what do we know about gravity and what do we still have questions about with gravity so that we can better go through this unit. So take a moment. Please pause the video at this time and go ahead and take a look at those 10 questions and just mark them with what you feel. If you feel like it's true, mark it true. If you feel like it's false, mark it false. And if you have no idea, just make a guess. Because again, this is a pre-learning activity. Don't expect you to know any of these things. Please go ahead and pause the video like I said now, and then unpause it once everyone's done completing these 10 questions. Okay, hopefully at this point you've answered the 10 questions. Again, if you haven't, just pause it real quick and do so. And now we're going to take a look at some of the answers to these questions. So again, this is a pre-learning activity, so I don't expect anyone to have gotten all these or any of these right. It's not here or there of whether what you know or what you don't know. But here's what we need to know about these things. These are things in science that are called misconceptions. They are things that sound like they are true, but in fact, they are actually all false. Okay, they're things that just kind of get stuck in our head that we have to work around so that we're not carrying any ideas into this unit. First off, if the Earth stopped spinning, we'd have plenty of problems, but gravity's not going to be affected by that. Half the Earth will get all the energy from the sun 100% of the time, and the other half will freeze. There's lots and lots of problems, but gravity is not going to be one of them. For the second one, there is gravity on the moon. It's just less than the gravity here that we have on Earth. So if you've ever seen any videos of astronauts on the moon, they kind of have to hop around a little bit instead of walking because the gravity is so much lower there. It's not easy to walk. For the third one, NASA trains for space in a number of different ways, but you can't ever turn off gravity. A really clever way that they train for space is using water, and you can make your buoyancy, how much you're floating and how much you're sinking, equal to each other, and that kind of simulates a space-like environment. They also have a really cool plane that they take real high up in the air, and then they go into a nosedive, and they start falling and falling and falling. And what eventually happens is you begin to fall within the plane as fast as the plane is falling. And so it kind of looks like you're floating around in the plane. You're really kind of plunging down. So luckily that plane will level out before it hits the ground. And then you feel the normal gravity that you would. But in that moment, when you're in free fall, it kind of looks kind of like outer space. That's how they filmed a lot of, I know this is going to sound old, but Apollo 13 and movies like that, where they do a lot of work in space. It was with the special plane that they just kind of take up and then they nosedive. And while you're nosediving, it kind of looks like you're in space. All right, the fourth one. It is not possible to shield the force of gravity by using lead. That's like something on a Superman or something like that. You can't stop gravity no matter what. Um, for the fifth one, Sir Isaac Newton did a lot of work with gravity. He was one of the first people to kind of mention it, to measure it, to figure out, what might affect gravity and things like that. But you can't discover something that's been around since the beginning of time. So it's more of a word thing on that. For the next one, you always have mass, but what you might not have in space is any weight. And we'll talk about the differences between mass and weight a little bit later. Again, for that next one, kind of going on, oops, nope. There is no gravity in space because you're far from the Earth. There is gravity in space. You're always going to experience gravity. It's just how much or how little gravity and from what sources. So there is gravity out in space. Weight is not measured in kilograms, it's measured in pounds. Mass is measured in kilograms. So we're going to learn more about that here in a little bit. And then there's no gravity in space because space is a vacuum. Space is a vacuum, but again, that doesn't have an effect on gravity. That's not what is causing gravity and things like that. So we'll get into that in a moment. And then if we pulled all the air out of this classroom, we wouldn't float around. There'd be a lot of problems. Your blood would boil, the gases, they would expand, you would pop, and it'd be a big mess, but we would still be stuck to the floor. Gravity's not going to be affected by that at all. All right, again, don't feel any type of way about this. This is just things that we were, had to get out of the way to make sure we weren't pulling them into this unit. So if you would, go ahead and flip back over to the front page and we will go over the lesson together. All right, first off, what is gravity? Now, as we just saw, we don't know everything there is to know about gravity. Number one, that's us. Number two, scientists still do not know everything there is to know about gravity. So we talk about it as the theory of gravitational attraction, but I want to make you careful of that word theory because here in science, theory is a much stronger word than you might use it in English or history or something like that. In English or history, a theory might be a good guess or a hunch. But in science, a theory is something that has been documented, that has been measured, that has followed the same patterns again and again and again. And we have a lot of support and idea about what's going on, but we just don't have 100% of it figured out. There's still some things that are a bit elusive, even to scientists, about gravity. But you never are going to jump out of the window and expect anything to happen but for you to fall to the ground. It's 1,000 out of 1,000 times that's going to happen. But even though we understand how gravity works for the most part and what things affect gravity, we still don't have a full idea. So that's why we still call it the theory of gravitational attraction. But again, what is gravity? Well, gravity is a weak force that exists between all objects. That means I have gravity. That means that you have your own gravity. That even means that the pen or pencil that you're working with right now has its own force of gravity. Now, obviously, we don't notice every little object's individual gravity, so there's some things that must affect how strong that gravity is. But anything that has mass will have gravity. And that's a really, really important concept to remember. Anything that has mass has gravity because that plays a very big role in how the universe comes together, which we'll talk about more about tomorrow. Now, here's the thing about gravity. Gravity is a weak force. Um, we do call it a weak force because it's not very strong, but we also call it a Goldilocks force. This is because gravity, if it was just a bit stronger, we don't exist because everything gets pulled into a black hole and no stars, no planets, no galaxies. But gravity, if it was just a little bit weaker than it currently is, then again, nothing exists because after the Big Bang, no atoms clump together, we don't get mass, we don't get planets, we don't get stars. So we call gravity a Goldilocks force because, like the story with Goldilocks and the Three Bears, she goes into one bed, it's too big, one bed's too small, the third one's just right. She eats all their food. She eats the porridge that's too hot, one's too cold, one's just right. So what I mean by Goldilocks is a force that's just right, just strong enough to pull things together, but it's not so strong that it pulls everything together. Now, obviously, we've already talked about the fact that gravity is not equal everywhere. So, what are some of the factors that affect how strong gravity is? The first is the size or mass. Mass is a better word to use here. The bigger the mass of an object, the stronger the force of gravity that object is going to exert. So, what we see here is a little example in pictures. We have two elephants and two mice. The elephants are going to experience a much stronger force of gravity to each other than the mice will because the elephants have more mass. The mice are much smaller, they have much less mass, and so they're going to have a weaker force of gravity between those two. So the bigger the mass, the stronger the force of gravity. This is what we call a direct relationship. As one goes up, so does the other. Now, we are obviously noticing the gravity of the Earth. That is much bigger than you or I. That's why we don't notice each other's gravity. And so the Earth pulls us down. But is the Earth the biggest object in our solar system? Well, obviously not. There's bigger planets, and there's something at the center of our solar system called the Sun, which is about 100 times the size of the Earth. So there are much more massive objects in our solar system. So here's the question. If mass affects gravity, and the bigger the mass, the stronger the gravity, why are we being pulled down to the Earth? Why aren't we being pulled out towards the sun or something that has a bigger mass and therefore a much stronger force of gravity? Well, that is because the second factor of gravity is the distance between the two objects. The closer two objects are to each other, the more they experience each other's gravity. But the farther apart two objects are from each other, the less they're going to experience their gravity. So if we take a look here, we have two ants that are very close together, and they're going to experience their gravity much stronger than the ants at the bottom of this slide, where they're much further apart. So which are we closer to? Are we closer to the Earth or are we closer to the sun? Well, we're obviously closer to the Earth. We're physically touching the Earth, which is why we've experienced the Earth's gravity pulling us down towards the center of the Earth. If you take a rocket ship and you go, away from the Earth, the further away from the Earth you get, the less of that gravity you experience until you get into outer space and you become, start floating around because you don't feel that force of gravity. So, this is what we call an inverse relationship because the bigger the distance, the less the force of gravity. So, as one goes up, the other goes down. The other one was a direct relationship. The bigger the mass, the bigger the gravity. But the greater the distance, the less the gravity you experience. So, like I said, we only notice the gravity of really big objects like planets, like the Earth itself. They have much more mass than anything that, we might be or be a part of. So we experience the Earth's gravity. Now, if we go deeper into outer space and we're further away from any stars or planets, then you might start to notice the gravity, your own gravity, or another object's gravity. But because we're close to the Earth, we're stuck here, we're being pulled down by that really big mass and that really big gravity. So, how does this idea work? What is the difference between mass? What is the difference between weight? And how does gravity affect this? Well, you don't actually have weight until you have a force of gravity. Okay. Weight is the force of gravity pulling you down. So when I step on the scale, that number that pops up is dependent on two things, my mass and the force of gravity of wherever I am. So here on the Earth, when I go and I step on the scale, it's going to read a certain number, which we won't talk about for reasons. But that is my downward force pushing down on the ground. Now, this is actually measured in newtons. There's a different calculation to figure out how many pounds that is. But your downward force is actually your weight. And again, Sir Isaac Newton did a lot of work with this and work with gravity. So that's why the unit is named after him, the Newton. Now, here's the thing. The best weight loss program in the world is just to go to outer space. Because when you go to outer space and you're far away from any stars or planets, your weight is going to drop to almost zero. Well, why is that? If I step on a scale out in deep space, why is my weight zero? Well, again, it has to do with that force of gravity. Objects do not have weight until they are experiencing gravity. And you're going to need to write that down. That's not going to pop up on the screen. So I'll say that one more time. Why does your weight drop to almost zero when you're deep in outer space? It's because there's no gravity pulling you down. In order to have weight, you must have gravity pulling you to a certain direction. That's going to give an object weight. So when you're far away from any big sources of gravity, guess what? You don't have any weight. Congratulations, you've done the best weight loss program in the world. The only problem is the second you step back down on Earth, you're going to go back to being the very same weight that you were because now you're experiencing Earth's gravity pulling you down. So where does mass fit into this whole situation? Well, weight is the pull of gravity on an object, whereas mass kind of counteracts that. It takes gravity out of the situation. It says how much stuff is there in an object. That is kind of the idea of mass. It's a measurement of how much material an object is made of. And we measure mass in kilograms. And we use a scale like the one shown on the screen, which is a digital scale. You may have also seen those triple beam balances in science classrooms from time to time. But here's the key. What do you have to do before you take the mass of something on the scale? You have to zero out the scale. And what that's doing is that's counteracting the force of gravity, taking that out of the equation. So all that you're left with is what material you were made of, your mass. So scales counteract gravity so that all you're weighing is the mass of the object, which is not going to be affected by the gravity of anything. So I have a mass of about 143 kilograms. That means if I take my mass here on Earth, I have a mass of 143 kilograms. If I go to the moon, I still have a mass of 143 kilograms. This is because I'm still made of the same amount of stuff, right? The same amount of blood, bones, hair, skin, all that that makes me me hasn't changed. The only thing that has changed is my location and therefore the force of gravity. When I step on a scale on the moon, my gravity, or excuse me, my weight is going to be much less because that force of gravity is much lower. But if I take my mass on the moon, because that's counteracting the gravity, my mass is going to be the same whether it's on the moon or the Earth or even deep in outer space. Deep in outer space, my weight is going to drop to almost zero. I'm going to become weightless because, again, there's no force of gravity pulling on my body. But my mass, the stuff that makes me me, hasn't changed. And so, therefore, I'm going to still be 143 kilograms. There's a little joke here, why this little astronaut feels sick. In case you didn't know, your digestive system has evolved to use gravity to its benefit. And which gravity? We're talking about the Earth's gravity. So when astronauts go into outer space, your body actually has some issues moving the food through your digestive system. And a lot of astronauts deal with issues of indigestion and stuff like that. So we are very much meant to be on this rock. All right. So again, just to keep these two straight, mass is how much material an object is made of, and the weight of an object is going to take its mass times the force of gravity. And again, you'll get that measurement out in newtons. So to calculate the weight of an object, all you have to do is you have to take the gravitational field strength, that is, what is the gravity in that area. And please go ahead and let's write this down somewhere on your paper, somewhere where you've got room. Earth's gravity, sorry, Earth's gravity is 9.8 meters per second squared. Okay. So the gravity here on Earth is 9.8, almost that perfect 10. So what I want you to do is I want you to write that down somewhere on your paper. So if I had a mass, I would take that number, I would multiply that by the 9.8 if you were trying to figure out what the weight was here on Earth, and that would tell you how many newtons of force I am pushing down on the ground with. Okay. So again, mass times gravity. So mass, whatever that mass number is, times the force of gravity will tell you an object's weight. Okay. So let me erase this real quick. All right. So again, here's the formula to calculate the weight of an object. You take its mass times the gravitational field strength. So, and that will give you the weight. Again, it is in newtons. So let's say we had an object with a mass of 45 kilograms. Well, if I want to know what the weight of that object was going to be, I would take that 45 kilograms and I would multiply it by the gravitational field strength of Earth, which is again 9.8. And that would tell me that it has 441 newtons of downward force. That's how much it's pushing down on the ground. Now, if we were going to go to the moon or if we were going to go to another planet, the only number that would change is this 9.8. It would change to a new number. I believe the moon is like 1.62, if I'm remembering correctly. And then different planets obviously have different strengths of gravity to their own. Bigger planets like Saturn or Jupiter are going to have a much stronger force of gravity than we do here on Earth, and much smaller planets like Mercury and others are going to have a much smaller gravity than that of Earth, which we're going to take a look at now. Um, okay. Okay, so now if there's time, we're going to go ahead and take a look at the how high you can jump. If there's not time, we'll stop the video here and dismiss. But if there is time, we're going to go ahead and go through this. If I am there or if it's with a teacher in person, they will guide you through the directions for this. But if not, I'm going to show you some numbers to use here that will help you at least get through the work and be able to get this grade for this. So, how high can you jump? We've all seen the videos of the Apollo astronauts playfully hopping around on the moon's surface. In this lab, you will jump here on Earth and compare that height with a jump on other objects in the solar system. Planets have varying amounts of molecules in their atmospheres. What do you think holds those molecules in place? Well, obviously, it's the force of gravity. So, what we're going to do here is we're going to take a jump, or an average of 3 jumps, and we're going to see what that jump would be like if we jumped on different planets and stuff in our solar system. So, what you're going to do is if you are not doing this in person, if you're doing this as like makeup or something like that, we're just going to use the jump and we're going to say it is 15 centimeters. Okay, so go ahead and write that on your paper, and that's going to be our average. If you're doing it as a lab in person, we'll do 3 jumps, and then we'll actually take an average of those jumps in order to do the numbers. But here's how you guys are going to do this if you are remote. So there's our jump of 15 centimeters. That's going to stay on the screen as I scroll down. And what we're going to do is we're going to take that number and we're going to do whatever it says in the operation column to figure out what would be the height of our jump on that other planet. Now, for Earth, it's just the same as what we just did. We jumped on Earth, so that is our direct number. So whatever it is, in this case, our 15 centimeters. And we're going to put that right here, 15 centimeters. Now, what you're going to do is you're always going to start with this number. All right, 100% of the time, you're going to start with your average, which is in this case the 15, and you're going to do whatever it tells you to do mathematically, and you're going to write that number down here. So we'll do the first one together. If we are going to take a look at what our jump would be on the sun, oops, excuse me, we're going to take our little handy dandy calculator. We're going to put in 15, and then we're going to do what it says to do. It says to divide it by 30. So 15 divided by 30. And that means we would be jumping 0.5 centimeters if we tried to jump on the sun. So right here, I would put a point and then 5. And do make sure you put your units of centimeters. And you're going to do that for each of these. So always start with your first number, in this case 15, and then do whatever it says. So for Mercury, it says multiply by 5 and then divide that number by 2. For Venus, we're going to multiply by 10 and then divide that number by 5. This is just working out the differences in gravity from Earth to these other objects in our solar system. Now, once you are done with that, okay, on the back, there are 3 kind of questions I want you to work through. For the first one on the analysis is just having you look at your numbers on that front page. Which one was the highest? Which one was the lowest? And why do you think that is? And then for number 2, it's kind of asking you to look at this chart. What they've done is they've taken Earth's gravity right here, and they have made it 1. We'll just call Earth 1. So any numbers bigger than 1, like Jupiter, that's how many more times Earth's gravity it is than Earth's gravity. If it's less than 1, like Mercury or Pluto or something like that, well, it's that many times lower than Earth's gravity. So what you're going to do is you're going to look at your numbers for, let's say, Mercury and Earth and Jupiter, and you're going to see, is there a pattern? When the number's big, what does that mean for your jump? When the number's small, what does that mean for your jump? And then finally, just go ahead and answer that third question with what do you think and why, and then we will be going over it as a class or turning it in for a grade. If there are any questions, please find myself or the teacher in the room to ask. But otherwise, go ahead and knock this out real quick, and then we will take a look at the exit tickets. You can go ahead and pause this video if you're working on it. I'm going to go ahead and pull up the exit ticket so we can talk through what an exit ticket is and how it works very briefly. Okay, it's the end of the first class, and what we see here is the first exit ticket, one of many. Remember, usually Mondays, Tuesdays, and Wednesdays, there's going to be exit tickets because those are new material days. There will not be an exit ticket after the quiz because we didn't learn anything new that day. So, what I like to use is I like to use a stoplight exit ticket. This is for both you and I to know how well you did by the end of every class. Hopefully, you know what the colors of the lights are on a stoplight and what they mean. The top section, that's the red section, they are kind of the basic level questions, and they're either circle and answer, true or false, or multiple choice, or maybe fill in a blank. If you are struggling with questions in the red section, red light means you need to stop, and you should probably stop and ask for help because you missed something kind of important that day. The second section, that's the yellow. Yellow is the intermediate level questions. Sometimes it might involve some math. It might involve, a sentence or so, maybe a list of words or a diagram to help answer these questions. They're worth 2 points apiece. And if you are struggling with questions in the yellow section, yellow means you're supposed to slow down and stop if needed. So you're going to slow down. What do I mean by that? Maybe take a look back over your notes or the assignments that we did that day to see if you can find yourself the answer. But if you need to, stop and ask for help. And then the green level question is the third level. That is the advanced level question. I'm going to be very honest. There are usually multiple parts to that last question. So to get all 3 points for that, you must answer all the different parts of that question. It's very important. So again, make sure you're reading through the question, you're answering all the parts, and then once you are done and it's all the way filled out, you may turn it in to myself or the teacher, and then you are free to go for that day, as long as it's close to the end of class. If it's a little early, I might ask you to just chill for a bit until I can dismiss. But things to keep in mind about this. Number one, this is not a quiz, so if you need help, ask for it. If you got your notes, use them. If you need to look something up on your phone, you can, but there are some differences sometimes between what I'm looking for and what the internet might tell you, so just be aware of that. And then the other thing I ask for you is no blanks. Because this is not a quiz, I don't want IDKs, I don't want blank answers. If you need help, you ask for it. I want some kind of answer for each question before I'll let you go. I grade these every day. They're out of 10 points. So if you get a 9 out of 10, you're still at an A. If you get an 8 out of 10, you're at a B. If you get a 7 out of 10, you're at a C, so on and so forth. And then usually I try and put little comments and stuff like that. If you miss something, I try to explain why or try and circle what you missed or things like that. But you'll get a score out of 10 and you'll get that back the next day. If you have questions or comments, again, please feel free to reach out and let me know. Otherwise, thank you guys for doing really well day one, and I will hope to see you day two. You guys have a great day.